All right, everyone, we are back, and we are going to solve one of our remaining problems, which is don't jump the gun. So you've all have probably seen some photos or some pictures where we have a sprinter that's in a sprinting stance, and I want to make sure that we don't have any false starts, that we don't jump the gun, so we can make our basically a next Olympics. So I have a sprinter with a mass of about 70 kilograms. The sprinter's wearing spikes, so the coefficient of friction between essentially the sprinter and the track is approximately 0.8. I want to see what is the maximum force that must be exerted on the runner to cause essentially that false start, or equivalently that they generate that could potentially cause a false start. So what's our first step in our problem-solving algorithm? Let's idealize our system. So we have a system as such. We can kind of imagine. So we have a sprinter. There's a centroid with a weight that's established there. And there's going to be some force that, again, we can just kind of idealize as that's being exerted on the sprinter to cause the false start or to initiate motion. So the impending motion obviously is in this direction here. And this is a pretty good idealized system. So let's go ahead and proceed, and what do we do next? Let's free the body. When we free the body, there's a lot of different forces that can occur here. So, and I could actually also include another one here, a force here. So we have these normal forces at both of the hands, both of the kind of feet here. You'll also have friction. Again, friction is tangent to the contact surface, and it's opposing the motion, so we'd have 1, 2, 3, 4 frictions. They'd all have the same equivalent, they'd all experience the same coefficient of friction, and we'd have to essentially solve that. Now, remember, one of the key things that we're trying to solve in these statics problems is to do what? Take a real system, we want to simplify it as much as we possibly can, but still represent how the system actually behaves. So, again, we can't do this because we're basically on YouTube, but if you get in the sprinter stance, one of the things that you'll notice if you're in a proper stance, the arm positions are really, there's not a lot of mass or essentially force that is being placed there. And if you look at the back foot and that front foot, really actually the first step that you're going to make is by actually taking that back foot and taking a very small step. So really, a lot of the force is being generated, or it's basically occurring, or you're holding a lot of the current mass in the static state at that front foot region. So let's simplify our system a little bit further. So let's say I only have a system that looks like this. So here, I'm just gonna have my normal force here, force in the 3 direction. Again, friction opposes the direction of motion. We have our angle, we have our mass. Let's go ahead and start solving now. And again, we had our coordinate system always at the beginning as well. So I'm going to, once again, I'm going to quit my kernel. I am going to also, I'm going to now go ahead and start to do some mass. So let's go ahead and the mass, let's go ahead and do sprinter. So my sprinter is going to be, the mass is going to be equal to 70 kilograms. Gravity is equal to 9.8. Weight is going to be equal to, actually we can see right there. Weight is equal to mass times gravity. What else do we know? We know the coefficient of friction is equal to 0.8. We know that my theta is equal to 21. And is that all? Yes, because we're asking for what is the force there. Actually, we can also define my F sub 3 is going to be equal to mu times F sub 2. So now, some of the force in the x direction are what? So I'm going to go minus F3 plus F1 times cosine of theta degree. You're all experts in this now. F sub y equals 0, set equal to, let's do F sub 1 times sine of theta degree, and then let's do minus W plus F2. So, how many unknowns? 2 equations, 2 unknowns. We're ready to go. All right, So let's go ahead and solve. Fx, Fy, and there we go. So actually, for this sprinter, it doesn't take actually a considerable amount of force. So again, one of the things that you have to ask yourself, is this a reasonable assumption that we built in? So, that's actually quite a small amount of force in order to kind of make that false start happen. But hey, perhaps it's true. Again, we'd have to actually measure it and actually do those things. So, but yeah, so no false starts, go win the gold medal. And I'll see you all in the next video. Thanks. Bye.